It is recording already. Okay, thanks. Do you have any questions on yesterday's course? No?
Excuse me, Professor.
Wait, the sound is very low. Yes, can you speak louder?
Yeah. Hello. I just couldn't find the recording of the sessions in any place. How we can access the link?
I don't know right now. Send me a mail later, okay?
Okay, thank you.
All right. So yesterday, where are my notes? So yesterday we discussed quite generic systems, okay, including the Ising model, the disordered version of the Ising model, the lattice gas, and then we started to discuss an even more generic class of models, okay, which are factor graphs. So we'll identify what I will call a factor graph, which will be really a graph representation that I will do now with the associated probability distribution. Okay, so let me call this type of probability distributions the factor graph or factorized distribution, but I prefer the name factor graph. Okay, so this XA is a subset of the variables. Generally, it is a few of them. And so the probability measure can be written as a product over these factors. We call also compatibility function. Okay, and then we did something very basic. We rewrote that in a Gibbs-Boltzmann form. Okay. If I want to make things even more clear, I can call this inverse log the energy of the eighth energy term. Okay. And this sum here defines an Hamiltonian. Okay. And so essentially what we just showed is that an extremely generic class of distributions, so these factors can be written as a Gibbs-Boltzmann distribution. Okay, so this is a kind of alternative way without calling at any moment statistical mechanics. Okay, we just define a generic class of distributions, and we just represent that in an exponential form, and naturally what appeared is a Gibbs-Boltzmann distribution. Okay, and so we identified this energy term, it's not a vector, which is 1 over, which is log 1 over FA, and we call that an energy. Why? Because you see that when the factor is satisfied, so the compatibility function is high, this inverse is low, okay? And so this log, because it's an increasing function, will be low as well. And so the energy is low, at least this energy contribution here, okay? While if FA is large, is low, the inverse is large, the log of something large is large, and therefore the energy will increase, so that the probability will be lower, okay? So each of these factors is trying to, each of these factors is constraining the configurations. Maybe some factors constrain in one way and others in another way. You can have contradictions, but overall, what matters is this whole distribution that gives a weight to a given configuration, which is the product over all factors. It takes into account all individual factors through this factorized form, through this product. Okay? All right. So let's consider an example. Here in the notes, I draw a random example. So let me actually show what is the factor graph. And here I emphasize graphical representation. Okay. So one factor graph could be, so the recipe is very easy. For each variable, each xi, you associate a node, okay? And each factor, fa, you associate a box, okay? And then you just connect these boxes to the nodes, to the variables on which they depend. Okay, so this is a function, this fa is a function of some nodes, of some variables. So you will draw edges like this that will be connected to the nodes on which they depend. While a given node will be connected to the factors which depend on this specific variable. Okay? So let's consider an example. This will be the variable x3, which will be connected to some factor that depends also on x6, which will be connected to another factor here, and to x4, which itself will be connected to a single factor, like this. And maybe this one is connected to another one here, that is connected to x5. Okay, that can be connected to another one. X3 is here, x2. Okay, so this is a graphical representation of a probability distribution. And even if we don't know precisely what are these functions at the moment, let's say these are generic functions, because this box here, this factor is connected to x3 and x6, whatever it is, we know that it is a function, I will call it f36 of x3 and x6. Okay? This will be a function of x5 only, so we call it f5, and so on and so forth. Okay? So even if you don't know what are the precise form of these functions, you know at least what is the dependency structure. Okay? And this is what is actually important. Okay? So, here in this case, this particular factor graph is associated to what Hamiltonian in general? Can you think 1 second? Can you write the Hamiltonian associated to this distribution? To this vector graph? Can you think about it?
The entire thing?
Yes. So this is associated to a factor distribution that you can write in exponential form. This defines an Hamiltonian. Okay. So think if this would be the factor graph associated to an Ising model. So in the Ising model, you have external fields that depend on single variables, okay, that act on single variables. And here you have pairwise interactions. And you can see directly from this graph that this is actually an Ising model. Because you see that factors are connected to at most 2 spins, 2 variables. Okay? So this is an Ising model. Can you write the associated Hamiltonian?
Yes.
So can you try? Particular size.
Should we just write F2, 3, 3, 4?
Don't use the notation F. So when I say the Hamiltonian of an Ising model, you can write this with external fields. Like there is a H1, H2, H3. If H1 and H2, H3 appear, and there are Jij's. Okay, J2, 3, for example.
And how do we tell the direction, like minus or plus?
So if J is a generic variable, it can have both sides, so it doesn't matter. Okay. So.
But isn't it going to be like very long?
It should be fine. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms.
Yeah.
Okay. It's okay. Try to write it to see if you understand really what it means, this object. And for those that manage to do it, try them for this one. And then you can try the red one also if you want. So it's an Ising model, but not anymore with just pairwise interactions. You have also 3 bodies interactions, even 4 bodies interactions. So is it clear what I mean when I say 2 bodies interactions or 3 bodies interaction?
Yes.
is it for you?
So for direct?
Yes.
Sorry.
So, for example, this is called a one-body interaction because it depends on a single variable. This is what we call also in physics an external magnetic field, a local field. Okay. This or this is one body. These are two bodies interactions. Okay, because they are pairwise interactions. They depend on two variables. This is a four-body interaction. Okay. You just need to count the number of edges that go out of the factor. And you know what's the number of variables on which it depends. And this is what we call four-body interactions, for example. Okay.
So where there are two, for example, F3, we can use J, and where there is only one, we use H.
Yeah.
When it comes to the four-body one,
You can also use J in general, yeah. You use whatever variable that you want, as long as those.
So it's different from the two-body and the one-body?
So usually in physics, for one-body interaction, we use a H to emphasize that it's a field, it's the usual notation in physics. And for two bodies, we use J. For more bodies interactions, J. But at the end, these are just symbols. What matters is the Hamiltonian. We don't care which symbol we use, but I prefer to use the standard notations. Okay, so for example, this first factor graph is corresponding to a probability distribution exponential minus hx over z, where the h is what? So let's look at, for example, this thing gives a minus h1 x1. Okay, that starts with the one-body interaction. We have a minus h2 x2 here. Then I put a minus h4 x4, minus h5 x5. Then we have two-body interactions here between x1 and x2. So this is the minus j12, x1, x2. Oops. Minus j23, x2, x3. Minus g34, x3, x4. And so on and so forth. This is a reionizing model. Okay. So in the same way, you can write the Hamiltonian associated with this factor graph. And you will get a number of terms. I will not write everything, but for example,
so,
yes.
Why there is the interaction of x2, even though it's connected to 3 points? Okay. So as I understand, the interaction depends on the boxes, on the factor, on the FA.
So these FAs, they represent the interactions, yes. So for example, if you want to write things in terms of the factors, this factor is an exponential minus h2 x2. While this thing in terms of factor. If you prefer to think in terms of factors, so that the measure is just the multiplication of the factors, this is also equivalent to think directly in the log domain, and therefore to think in terms of the Hamiltonian. Okay, so to think about the exponent in the probability measure instead of the exponential of the exponent, that's the same. So if you want this factor here is an exponent, oops, it's an exponent, what happens? It's an exponent. Okay, I cannot write anymore. Okay. Exponential j minus. No, sorry, there is no this minus is not here because the minus, this minus simplifies with these minuses. Okay, so but if you write in terms of factors, you don't need this minus. So this factor here is an exponential of j 34 x3 x4. Okay. This factor here is exponential j36 x3 x6. Okay. And you make the product of all these exponentials, and you get the Gibbs-Boltzmann distribution. Okay. Or if you prefer, you think directly in terms of this energy, which is the same. So each term here is indeed minus the log of 1 over a given factor. Okay?
Can I?
Yes.
So, for this graph, not all x will have a single factor because x3 and x6 they all have interaction.
Sorry, the question is not clear.
For this factor graph,
Yes.
not all
of them have an external field. Yeah.
yes. And for the red factor graph, for example, 3, 4, and 6, they are connected. Is it that can we read that way? And also 3 and 6 are connected differently when they compared to how 3, 6, and 4 are connected.
Yeah, I don't understand the question.
So the factor of the interaction.
So the red factor graph.
Yes.
Okay.
Between 3 and 6.
Okay, so this thing.
Yes.
Yes.
From the factor among 3, 4, and 6.
This one.
Yeah.
Yeah.
So it's different when.
Yeah, if you have two boxes, it means you have two different functions. Here you have two different functions, and both of them depend on 3 and 6. But this one depends on 3, 6, and 4. Okay?
So we should view it in terms of the boxes or the SA. Than the interaction between the circles. So, for 3, 4, and 6, they are interacting together.
Yes, yes. You see that there are boxes that connect them, so you have interactions.
So,
as long as you have a factor that depends on both of these variables, then they interact through this function.
so without 6, 3 and 4 cannot interact. Can I do it that way?
So you mean if I erase 6? Then
3
what?
and 4 will not be connected.
No, but I cannot just erase 6 like this and keep these factors, for example, because these functions depend on 3 variables. So I need to redefine this function if I erase the node. I cannot just erase a node and, you see, like these functions are depending on 3 arguments. So I can, what does it mean if I remove an argument? I need to redefine functions. You see. But you can have if this was not there, maybe you could have another factor here like this. You can write the factor graph that you want. It's totally generic. Does it answer your question or?
Yes.
Sorry, someone is insisting to call me. Maybe there is something urgent. Sorry. Sì, pronto? Ah sì, scusa, chiama dopo sto insegnando, grazie. Ciao. Okay, is it clear? Yeah. All right. So in the first week, you had one approach to the fundamental object that we're studying in equilibrium statistical mechanics, which is the Gibbs-Bosman distribution, okay, which was through the definition of ensemble, the canonical ensemble, and we just obtained the same type of distribution from a totally different approach, okay, a more abstract approach of just stating a generic form of quality distributions that can just be rewritten in the same form as the Gibbs-Bosman distribution. But it looks like a very simple observation, almost trivial, but actually it opens it paves the way to use statistical mechanics tools for much more abstract and different problems than just particles in a box. Okay. Or another way to see it is that you can problems coming from computer science, from very many different disciplines, can be also thought in a sense as particles in a box, because they are described by the same type of probability measures. Okay. All right, is it here that I wanted to see? Maybe I wanted to give you an example here, a nice example of an application of a factor graph. Have you ever heard about error correcting codes? Error correcting codes.
Error correcting
Codes, yes. So an error correcting code is something that you're using 20,000 times a day, without knowing it, which is an algorithm that is used for communication. So when you're trying to communicate information with someone, we don't really know yet what is information, but let's say our vague idea at the moment are bits. Okay, it's a series of symbols. So let's say zeros and ones that you're trying to communicate with someone. These bits, they will travel through, for example, the air before reaching some satellite that will then deviate the signal and send it towards the receiver. Okay, something like that, or through some cable or whatever. Okay, so the signal, these bits, they carry through what we call a communication channel. Okay, which is the medium through which they are transmitted. And there exists no way to communicate without noise, without errors. It means that whatever you transmit, there will be in some way some corruption of these bits. Okay, some errors will appear. Okay, so error correcting codes are algorithms that receive a noisy version of these bits. By noisy, it means a corrupted version of these bits where errors appeared, and is trying to decode, so to find what was the original signal, so to correct the errors. So it's an error correcting code. Okay? So actually the whole theory of modern error correcting codes and the type of algorithms that are actually used in your phones are based on this formalism of factor graphs. Okay? And these factor graphs are extremely practical to represent some of the top error correcting codes, and independently of the algorithm, what we call the codes, that is the way we will constrain the bits so that on the receiver side, the receiver can decode. So I will make clear what I'm saying right now. So okay, let me give an example with your parenthesis, okay? Error, oops. But I think it's a nice application. It's also so that you start to understand that all these tools are not just for studying Ising models, or the other way around. Ising models are so general that you can even study error corrections in communication. So error correcting code, error correction. And here I will present quickly what we call low density parity, or let's forget the low density. So often you see low density, and I will tell what low density means here, but what is important is parity check code. This is often called LDPCs, low density parity check code. And this is actually the technology used by your phone for 4G. So the idea is very simple. So let's first think about a very simple model of noise, of communication channel. Let's say that when you have a bit xi that belongs to 0, 1, okay? When it is communicated through the communication channel, on the other side you receive a yi, and we will say in the simplest setting that it is equal to xi with probability one minus epsilon, and it is minus xi with proba epsilon. Okay? So this channel, this communication channel, is called a BSC epsilon, where BSC stands for binary symmetric channel. And this channel is just something that, with a certain probability epsilon, flips the bit. So it creates an error. And sorry, here we are considering, so in this case, no. So then I want to consider, so let me say, we will do even simpler. Okay. Let's do something simpler. We will do question mark. Otherwise, you have to consider spins, -1 and 1, otherwise the flip. We can consider two models. There is this one. No, let me consider really the simplest model first. I will call the BEC epsilon. This is the binary eraser channel, which is really the simplest model. So with probability 1 epsilon, 1 minus epsilon, the bit is perfectly transmitted. Okay. And with probability epsilon, you receive nothing. The bit is erased. Okay, this is what I mean by question mark. You receive nothing. Okay? So now imagine that you want to send a sequence of bits like this. Okay? you see that when this will be communicated, what you will receive is something like this. For example, okay. So in expectation, you will have a fraction epsilon n. If there are n bits here, there will be approximately epsilon n of them erased. Okay? So for this, the information will be totally lost. So in some way, we need to find a smart way to represent this string of bits, which is the information we want to transmit, so that even if mistakes appear, on the other side, we are still able to find back the missing bits. So we need a code. We need in some way to start from this series of bits that are independent of each other. Here, if there are no constraints on these bits, if you receive a bit, the next one can be anything, a priori. What we'll do instead is to create a code. It means that we will constrain. We will say that these bits are constrained in some way. So what I mean by that is that you can create a code. Let me call it C, which will be represented. So what is the best way to say it to you directly? I will. Okay, so the code will be the ensemble of binary strings such that, and here you put whatever constraints you want, and the type of constraints will be called parity checks. So what do we mean? We mean, for example, one constraint could be that the bits, so the bits are the xi, x1 plus x3 plus x7, let's say, is 0. So these plus here are called the XOR operation. Essentially, it just does the sum and gives you a 1 if the sum is odd, and it gives you a 0 if the sum is even. It's a mod 2, it's the sum modulo 2. Okay? So essentially, this constraint here is enforcing the sum of the first bit plus third bit and seventh bit to be an even number. So this is equivalent to say x1 plus x3 plus x7 is even. Okay? So this could be one constraint, but then you could have many like this. Let's say x3 plus x37 plus x102 is 0, and so on and so forth. Okay? So this is a huge set. If you have many constraints and many bits, we will assume that the strings that we want to send are large. Okay? This defines a huge set of binary strings, okay, of sequences of bits, but not all of them, okay? Some particular ones, only the bits, the sequences of bits that verify these specific constraints, okay? And actually you can represent that with a factor graph. Okay, so let's say that we have a very simple binary string, which is just x1, x2, x3, x4, okay? And our code will be the set of x's such that, let's say x1 plus x2 is 0, x1 plus x3 plus x4 is 0, and I don't know, so here 2 enters there already. 3, let's say x3 plus x1 is 0. Okay.
I have a question.
Yes.
Isn't the So we're doing a parity check, right? Adding the parity bit to the...
Yes, these constraints are called parity checks. Because it checks, this constraint checks the parity of the subset of bits, yes.
So if it's even, it's 0, and if it's odd, it's 1?
No, so this constraint, the fact that the sum modulo 2 or the XOR operation between these bits is equal to 0 is the same as saying I want the sum of these bits to be even. If you want, this parity check can be equivalently written as an indicator function if x1 plus x3 plus x4 is even. That's the same thing. Okay? Maybe this is a nicer representation.
We choose the bit randomly or...
So the way you create the code is your design. Okay, this is the choice of the people that create codes. But actually there is a whole theory behind that. It appears something quite beautiful is that if you generate a random set of constraints, the sense that you create parity checks randomly, the sense that you connect some of these bits in a random way through parity checks, in the large limit where you have many bits, this type of codes may become optimal. You can reach the highest communication performance. You don't need to be precise in the way you design. You don't need to have a deterministic design. You can recreate a random code, and this will be extremely efficient. But in general, this is your choice. Okay, here I wrote a random parity checks. Okay, so what is the factor graph representation of that? And so first, what is the factor graph distribution associated to that? Okay, so the probability that x, the probability, so we place ourselves at the receiver side. What is the probability if I receive something that it is actually a code word? It is just the product of these factors. So here it is just 1 if x1 plus x2 even times 1 x1 plus x3 plus x4 even times 1 x3 plus x1 even. Okay, divided by z. And z here is what? It is the cardinal of this code. It is the number of binary strings that verify these constraints. So essentially all what we call code words, that means binary strings inside the code that belong to the code, they're equally probable from this a priori, okay? As long as they verify these constraints, they're valid code word, okay? Now, of course, so how do we represent that in a factor, with a factor graph? So let me put x1 here, x2 here, x3 here, and x4 here. So we have a parity check that connects x1 and x2. So I have a constraint here, and this constraint is this. Okay. Then we have a 3 and 4. Then we have a 1, 3, 4. And 3 and 1. Okay. So that's, if you want, that's a factor representation of a valid code word. Okay. So now Yes.
Shouldn't there be blocks in the middle of 1 and 3 as well?
1, 2, 1, 3, 4, 1.
Yes, the 1 and 3 are unaffected.
Yes.
But not 3 and 4.
And 1 and 3, and not 3 and 4, yes.
Not 3 and 4. Yeah. And also a bit of the middle. Yeah, the middle box should be end of middle.
Sorry, so wait.
Yeah.
1, 2, 1, oops,
We connect to from 3.
1, 3, 4.
Yeah.
Okay, so this represents a valid code word. Okay. Now, do I want to say that now, or okay, exercise for tomorrow. Okay, then I will discuss that. It's not a trivial exercise. Try to think about that. So if you receive at the receiver side, you receive a series of bits. So, by the way, when we do communications, at the transmitter and receiver side, before communicating, we agree on a code. Okay? It means that whatever I will receive as a series of bits, I know that it has to belong to the code. It has to be a valid code word. Okay? So it must be a series of bits that verify these constraints. And these constraints were agreed before communicating between the receiver and the transmitter. So you see that if this code is extremely large, whatever word you can think of, you can map it to one of the code words. Okay, so you can represent the words in English or whatever language, you can map each of them to a series of bits in the code, and so if the code is large enough, okay. So now the question here, what we wrote is a representation of what is a valid code word, okay? It's the factor graph associated to what is a valid code word, okay? But now, the question I ask you is, if you receive at the receiver side a series of bits, so here we said, let's say in general, y1, y2, until yn, okay? This is the received noisy code word, okay? Can you try to guess what is the probability that the code word X has been sent? Let's say that X has been transmitted. Given, you remember, this is the conditioning operation, given that Y has been received. Okay? So the hint here is that you need to use base formula. Okay? And you know two things. So you know in base formula, you remember we know that the P of X given Y, the posterior distribution, okay, is what? Is P of X times P of Y given X divided by a normalization, which is also the probability of Y, but I call it Z. to stay in the statistical mechanics framework. Okay, it's just a normalization. So here, I already gave you one part of this object. Okay, I gave you the P of X. We know that this probability anyway has to be 0 if the X is not a valid code word. Okay? Because only code words can be transmitted. Okay? So if you want, you can think of this distribution as a prior distribution that gives an a priori weight to the possible X's, the possible signals, the possible information that has been transmitted. Okay. Now, what you need to think about is what is this part, which is also called the likelihood. Okay. This is the likelihood of the data, of the received data, in this case a noisy code word, given that the transmitted information was X. Okay? So how to get this thing? What you have to think about is that I told you the rule of how a given entry of Y is generated conditioned on the given bit. We said that Yi is equal to Xi with probability 1 minus epsilon, and it is a question mark with probability epsilon. Okay? So this Y that you receive, it is essentially a series of bits, 1, 0, zeros, question mark, zeros, 1, question mark, and so on. You received this given series of symbols, which are OR bits. When you know that you receive a bit, it cannot be a mistake. It is what it is. But when you receive a question mark, you don't know. Okay. So how can you combine this information, this noisy code word that you received, with the prior here, which is the rule that encodes, that represents the code, okay, together to get the probability that a given code word is X, given that you received Y. So try to think how to design this function here. It's called the likelihood. Okay. And here what is important also is that these Yi's, you see they're independent, conditioned on the Xi's, they're independent. Each Yi only depends on one given Xi. Okay? Which means in a sense that this probability of Y even X should be written as a product of I of some P of Yi given Xi. So now the question is, what is this function? I essentially gave you almost everything. Now we have to think about that. Okay? But you see, and second question, so once you have done that, once get this posterior distribution, second question, draw the associated factor graph. Because the factor graph that we drew before was only the one for P of X. This one will be maybe different because it's not the same probability distribution. And when I say draw the factor graph, the associated factor graph, I mean, in this case, consider a simple example like this, for example. Choose the example you want, define a small code, or use this example that I wrote there, and draw a small factor graph. Doesn't just to make sure you understand what you're doing. Okay. don't consider the generic examples with the n variables and try to write something that's the size of the wall. That's not the point, okay? So, is it even if here this step is not clear yet, and the exercise is for you to think a bit about that, but is the idea clear? In a sense, is the problem clear?
Yes.
Yes?
We also consider the given code.
The what?
The given code from the previous.
You can consider the previous code, or no, for writing base formula here to get the posterior distribution of the code word given the noisy code word, I would like you to write that in general.
In general.
In general.
Okay.
So for n variables, so just to write that really for with x and y which are generic, not for specific, not for a specific code, for a generic parity check code. Okay.
Given those probabilities, right?
Given this model here.
Yeah.
Yes, given this model, given the binary eraser channel. Okay. But then you can write this probability distribution generically for any parity checks. You can write the generic form. Okay. If you have troubles with that, maybe you can write it for a specific example for this simple code and then generalize if you want. So you see that with this simple graphical representation, actually you can start to tackle extremely complex problems. You can, draw a very complex probability distributions that are useful in many contexts, including in inference. Inference means in general reconstructing signals from noisy data about this signal, okay, which is the case here. The signal is the strings of bits that is transmitted, and the noisy data is the noisy code word, is the corrupted version of this signal. Okay, and inference is about writing probability distributions of signals given data about these signals, and this is exactly what we're doing right now. Okay, and then once you have written this probability distribution, essentially algorithms, they're trying to find, for example, what is the most probable code word with respect to this distribution. Okay, once you wrote this distribution, what would be the natural estimator? So I'm saying many things that I didn't plan to say, but it's fine. What is, when we put an at like this, we mean in inference, we mean an estimator of some signal. What we believe is the signal once we exploited the data. Okay? So an estimator, a natural one, could be the argmax of this probability distribution. That is what we call also the mode. The mode of a distribution is the argument that maximizes it. Okay? So the estimator in this case would be the most probable code word given the data we received. Okay, which is quite natural. Okay, and then solving this optimization problem may be extremely complicated. This is not what I want to discuss now, and that's a whole field in itself. That's error correction, and we need efficient algorithms. What I mean is that solving, then once you can write these complicated probability distributions, but then actually using these complicated probability distributions to do inference, like finding their maximum or computing means, expectations with respect to these distributions, are very difficult. And this is an old field, and there are algorithms about that, and if you want to know about that, you can ask me with pleasure. We won't discuss that, that's not the point here. Okay? But the first thing is to understand that you can use this statistical physics framework, or this more generic Bayesian, we call that Bayesian inference framework, which is just to write posterior distributions like we did, to perform inference. Okay. Okay. right, so now what I want to do is to drink a bit of water, and then we will discuss the most important quantity in information theory, which is called the entropy, the channel entropy. Okay, so now we enter a new chapter, if you want. By the way, if some of the things I said here are not totally clear, also, I tried to be pedagogical about those very same kind of things I said right now in this article I sent you. Okay, there is a lot about the base formula, the base formula, the interpretation of this prior and what I call the likelihood here. So if you are interested, I suggest you to maybe have a look. And also about the entropy that we'll discuss now. Essentially in the article there is a summarized version of what I will say now. So this is all right, so what is, for you, the entropy? So the entropy, you've heard about it in statistical mechanics. We'll approach it through a different angle, the information theory. But do you have an idea about what is entropy? How would you say in a few words? What does it mean for you? Physically, I guess, because this is where you learn what entropy is in physics. Do you have a feeling of what it is, or? Yes. Disorder.
Disorder. For example, so we came here. It's a non-physics example.
I love non-physics examples, so I'm happy with that.
We got used to a routine for 14 days and boom, we went out, and it was extremely cold on 5 days. We didn't know what it does. The locals didn't know what it does.
Okay.
And then it got hot, and now it's, we just don't know what's going to happen, so disorder is increasing. The uncertainty is kind of increasing because we have less time, we have more study. So.
There is a very, there is a word that you use that is extremely connected, that we use a lot, which is uncertainty.
Yeah.
So I prefer the word uncertainty actually than disorder, which it's connected, of course. But yeah, it is actually a measure of uncertainty. But actually, you can also interpret it as a measure of information content of some random variable. So let's try to understand why these apparently two different definitions that seems to oppose themselves are actually the same thing. There is no paradox, and this is what I want to try to convey in the next table. Okay, so let's try to understand what is entropy. So entropy, indeed, if you start statistical physics course, and what we tell you about is a kind of measure of the randomness of the system. It quantifies, in a sense, the randomness of the system, in the sense that, for example, in the simplest setting, which is the microcanonical ensemble, what is the formula for the entropy? Which is actually the very first formula of entropy, which is the Boltzmann entropy, defined for the microcanonical ensemble. Do you remember the definition?
In where temperature?
Omega.
Yes, it's log of omega, and what is omega?
A number of possible.
Yeah, but
The number of microstates.
yes. So we have specific words in statistical mechanics. So it's called microstates. Okay. So indeed, in the microcanonical ensemble, the entropy is defined as the logarithm of the number of microstates. Okay. Microstates are the states accessible to the system. Okay. So it essentially counts the number of microstates, but then you take a log. And why is it natural to take a log? Because in complex systems, usually the number of microstates grows exponentially. Okay? So what matters, what we want is to have a quantity because it grows exponentially with the number of particles. Okay, so instead of dealing with extremely large quantities, because exponential of something proportional to n diverges at a tremendous speed, exponentially fast. So you will like to take logs so that the quantities are nicer to work with. Okay? So that they become, we say, extensive. They scale with the n. Easy. Okay. All right, so I will forget all that. Maybe at some point we'll come back to the connection between the information theoretic and statistical mechanics interpretation. But right now what I want to do is to start from Shannon definition, which is a priori not connected to statistical mechanics, and to see what it means. Okay, have you ever heard about this name, Claude Shannon? So Claude Shannon is one of the geniuses of the century. He was an engineer at Bell Labs at this time. Okay. And in 1948, he published a paper which was the birth of information theory. And in particular, he defined, actually this quantity appeared before, but then he understood, he proved that this is the proper definition of information content. And we will see what it means, information content. So the Shannon entropy is defined for a discrete, I will always consider the discrete case, and like I said already at the beginning, for a discrete random variable. So consider an ensemble. Like we said, it is a random variable. It's space, or it's space of possible configurations, and the probability distribution. The entropy of X, which is also sometimes defined as the entropy of the distribution of X, that's the same, is what? It's the sum over all configurations, over all possible outcomes of this random variable of P of X log of 1 of P of X. And sometimes, instead of taking a log, in which case the entropy is in units of what we call nats. Nats is therefore natural units. But if instead you use the log 2, the log in base 2, the entropy is in bits. Is it clear for everyone what a log 2 is?
Yes.
Okay, the log 2 of something is the log of this thing divided by the log of 2. All right. Okay. So this is the entropy, so it doesn't look like a too nasty object. And you see that here, what is this operation? It's an expectation. Okay, so this is also the expectation. Which symbol did I use? I introduced the bracket. Huh? This is the expectation of what I will call h of x with respect to the distribution P, where h of x is log of 1 over px. Okay. And this quantity is called the information content of outcome X. And this is also called the surprise. So let's try to understand why did we give this name, why Sean gave these names to this quantity. Actually, the interpretation is very close to what we already said with these factors. Okay? So first notice that this h of x is what? Is always non-negative. Okay? Because in the discrete case, the probability of x is a number between 0 and 1. It's a positive number, so 1 over px is positive and greater than 1. 1 over px is greater than 1. And the log of something greater than 1 is positive. Yes or no? Okay, in case of, the log looks like this. Here you have 1. Okay, and here it goes to 0. It goes, sorry, to minus infinity in 0 plus. Yeah. So, like we're physicists, so as usual we look at extremes in order to understand what happens. Okay. So let's consider the extreme case where the probability of a given outcome is very high. It's very close to 1. Okay. Then 1 divided by something very close to 1 is essentially 1. And the log of something close to 1 is almost 0, tends to 0 plus. Okay? So you see that if an outcome has a very high probability, then its associated surprise is low. Okay? And also its information content is low. It's just saying the same thing. In which sense? Let's say that I tell you the outcome of something which was extremely predictable. For example, I'll tell you, by the way, tomorrow morning, the sun will rise. This event is a random variable, because maybe the sun will not rise. Okay? But actually it has probability which is so high that the fact that I tell you, if I'm God and I know that actually the sun will rise, I tell you this information, you gain essentially no information because you knew it already, because the probability of this thing was so high anyway that you had no doubt about that. So the information content of this thing, of this outcome, of this random variable, where the random variable here is whether the sun will rise or not, is very low. Or equivalently, the associated surprise is very low. When you see the sun rising, it's not so surprising. It was extremely expected in the sense that it has very high probability to happen. Okay? And so the Shannon entropy is the expected surprise or the expected information content of a random variable. So you average the information content over all possible outcomes. Okay?
So
Yes.
that means if the expectation is 0, that means actually the information is not important.
So, in which case can it be 0? So let's take the. So I will answer your question. Let's first take the second extreme, which is related to your question. if P of X now is very low, so it's very close to 0, then 1 over something very close to 0 tends to infinity. The log is increasing, so the associated information content or surprise is very high. If you observe an extremely improbable outcome of some random variable, it leads to a very high surprise. It was not expected at all. It had very low probability to happen. And also the associated information content is very high. So let's consider 2 examples. So I already gave you one with the sun, okay? Let's continue on this example before giving others. Let's imagine that one day the sun does not rise, okay? This event has a probability which is so low that if it happens, it will be the end of the world. Everyone gets scared, it will be the revolution, okay? The world as we know it is over. Because the surprise is so high, okay, that everyone will get scared, okay? It would be extremely surprising not to see the sun rising, because it has a very low probability to happen, okay? Let's consider another example. So let's imagine you're in the desert like this, and suddenly, it rains crazy, and it even rains frogs, okay, that talk to you, okay, playing guitars. So this event, which is the outcome of some random variable, where here the random variable was the weather, okay? This outcome is so improbable, it has so low probability that the associated surprise is tremendous. Okay, you will be extremely surprised to observe that. And the associated information content is therefore also very high. And in this case, you should realize from that information that you're dreaming, essentially. Okay? So this outcome is so improbable that it brings to you a lot of information. In this case, that you're not awake. Okay? Or if you take the ticket of the lottery, if I tell you your ticket is not the winning one, it will not be very surprising, because this was expected. So the information content of this piece of information, okay, is low. Now if I tell you this is a winning one, you will be extremely surprised, and the associated information content is very high. In this case, it will convert it into a high amount of money. Okay? Is it clear, the interpretation of this object now? And you see that it's the same, it's similar to the interpretation we gave about the factor. When the factor was happy, its log was increasing. So you see, it's the same structure appearing here. Okay? Okay, so now I would like to emphasize the fact that what I will say will sound a bit paradoxal and it will sound strange, but actually it is totally coherent with the interpretation that we discussed already. You can also interpret the entropy as a measure of uncertainty, okay, which is closer to the interpretation in statistical mechanics. Okay, this is the first thing you said. The entropy in statistical mechanics is a measure of the disorder, of the uncertainty about which microstates in which you are. Okay? And from this definition, we can also interpret that as a measure of uncertainty, which sounds the opposite of information content, a priori. Okay? But it is not. Why? This is just a matter of conceptually placing yourself before observing the outcome of the random variable or after having observed it. What do I mean by that? The interpretation in terms of information content or surprise is really correct when you place yourself after observation of the outcome. Okay, in all the examples that we discussed, something happened and you were surprised, or the information content associated to this observation was high. So we were placing ourselves after the observation of the outcome of the random variable. Okay? But if you place yourself before the observation, then the natural interpretation is in terms of a measure of uncertainty. Okay? If an outcome has very high probability, again, this h of x will be low, and therefore the uncertainty about this outcome is indeed low. If it has high probability before that it happens, you would bet on the fact that it will happen. So your uncertainty about whether this will happen or not is low. Okay? If instead some outcome has very low probability, your uncertainty about the fact that it will occur is extremely high. You would never bet that something with very low probability will happen. And so you have a very high uncertainty about that. So you see, you can or interpret that as an information gain when you observe a given outcome, or as a measure of your uncertainty about whether this outcome will happen or not. It's just placing yourself conceptually before or after the observation of the actual outcome of the random variable. Okay? So actually, information and uncertainty are fundamentally the same thing. Okay? And so the channel entropy is the expectation of this information content or about this uncertainty. Okay? In terms of uncertainty, this is your average uncertainty about the system. So all that is written in what I wrote, so you can process it again. All that is not trivial to grasp, okay? So think about it. Can you compute the entropy of a fair coin and of a biased coin? Let's say it's the coin that has, fair coin is probability 1/2 to be head or tail, and a biased coin that has probability, let's say, in what I wrote, 9/10 to be head. So we have two random variables. I would like you to compute the entropy of both. But before computing anything, do you think that the entropy associated to the fair coin will be higher or lower than the one associated to the biased coin? With the interpretations that we discussed now.
What's the bias coin?
A biased coin, in this sense, is a coin that has statistically 9 chances over 10 to fall on head, for example.
Yeah.
Okay.
The biased one have lower entropy.
The biased has lower entropy.
Yes.
Why?
Because we are almost certain that it will always give us a head.
We are almost certain in the sense that we are.
Yeah.
There is probability 9. Okay, I agree with you. So the surprise about the outcome of the biased coin is in average lower, because most of the time it will fall on the one which is expected, which is head. Okay. But you see that sometimes it will fall on tail, in which case the information content is high. So a priori it could balance the low information content of the other event. But the fact that you have a logarithm here, which is a concave function, essentially lowers down, in a sense, the weight associated to this very surprising event. What matters, because we take an average, the entropy will be higher if most outcomes have not so high, not so low surprise, rather than having many outcomes with a low surprise and one or two with a very high surprise. The average and the entropy will be higher in the case where the distribution is closer to uniform. Okay? Because of course this is for a uniform random variable that you have less predictability because things are uniform. And this is a measure of uncertainty, which is the same thing as unpredictability. This is the same word. And of course, the unpredictability is the highest in the case where the distribution is flat, it's uniform. And actually, we try to prove it. So compute the entropy for the biased and fair coin. You can do it now, you need 3 minutes. And then try to prove that the entropy is maximized for the uniform distribution.
I have a question, sir.
Yes.
So, can we say that if a distribution has a minimum standard deviation, it means that it has a minimum entropy? I mean, is it equivalent? It is an equivalence all the time?
Between what and what? Between low entropy and?
And the lowest standard deviation.
No, it is the opposite. I'm right now saying that when the distribution is flat, is uniform,
yes,
it has higher entropy than when the distribution is peaked.
Yeah, yeah.
So when the distribution is peaked, it has a low standard deviation. So it is the opposite of what you said. When the standard deviation, the variance is small, then the entropy will be small.
Yeah, but my question is this correct always?
Yes, but you said the opposite.
Ah, okay. I meant it like you said.
Okay. Yes, generally, so the two extremes, again, we're physicists, so we look at the two extremes. The case where the entropy is the highest, which is what you should try to prove right now, is when the distribution is flat, when the distribution is uniform over all outcomes. And I would like to know, in this case, what is the entropy, what is the formula? Okay, let's say that you have cardinal of calligraphic X outcomes, which is the cardinal of the configuration space for this random variable. Can you give me the entropy as a function of this object? And the other extreme case is when the random variable is not random, is deterministic. What does it mean? It means that one of the outcomes has probability 1 and all the others have probability 0. So I would like you to compute the entropy in these two cases. If you're stuck, tell me. Huh? So what is the entropy of these two coins? Do you have that already?
I have a question. So, for example, probability of head is 1 by 2 in a square point. Is that P of X? Like, do you have to take the log of that? 1 over that. Like, P of, that is the log of P.
You just have to use this formula, yeah. Then take the log in log 2, compute fixed in bits.
But with the biased ones, are there 10 outcomes? No, there are only 2 outcomes.
There are 2 outcomes.
So the cardinality is still 2.
Yeah, there are 2 outcomes.
Okay. That's kind of confusing.
And maybe you can use your phone then to compute the actual number to get the number. Because you can just write the formula, but then to get the number to then discuss it. This is one of the few times this year where you will actually need to compute an actual number. And when we do theoretical physics, we mostly work with symbols. Okay, so the X, the fair coin, so this symbol here means is distributed according to which distribution? What is the distribution of a fair coin? This I know you know because this is the first thing you did with Roman. It's a Bernoulli distribution of parameter 1/2. So we are asking ourselves what is the entropy of this probability distribution. So we use our formula. It is H x pair is the probability of the first outcome, which is 1/2, times log 2 of 1 over 1/2, which is 2, plus the same thing. So actually, this is just log 2 in base 2, which is 1. So a fair coin is like a random bit. It has entropy of 1 bit. Okay? And actually, from this also, we see another, which is actually totally connected to what we discussed before, but another nice interpretation of the entropy written in log 2 base, in bits, is the expected number of binary questions, of yes-no questions, where both yes and no have a priori the same probability, that you need to ask in order to predict the outcome of this random variable. Okay? Or said equivalently, if you observe the outcome of a random variable with an entropy x, well, with an entropy h of x, is the number of yes-no questions, the expected number of yes-no questions answered by the outcome of x. So we understood that the entropy was a measure of information content. Okay, this is the expected gain of information we obtain when we measure, when we observe the outcome of a random variable. Okay, you remember we discussed that. But you can, any information, you can also think of it as a series of answers to yes-no questions. Okay? For example, if we're playing a game where you have to guess who I have in mind, the random variable is the person I have in mind. It has a billion possible outcomes, or let's say if we think about, if we restrict that to famous actors from the 60s. I don't know. Maybe there are 200 people we have in mind. The number of outcomes is 200. But you can also see that the information that you gain when you guess who I have in mind is the same amount of information as a yes or no answer to binary questions, because this game is played how? You tell me, do you think about this person? I say no, restrict a bit. Then do you think about this person? No. Okay, until you converge. So the information you gain can be seen as a series of answers to yes-no questions. A series of results of outcomes of a coin. Okay. So another nice interpretation of the entropy is exactly this: is the number of, in expectation, the number of binary questions that have been answered when you observe a given outcome. Or equivalently, if you place yourself before the actual observation, is the expected number of binary questions you need to ask in order to predict in advance the outcome of this random variable. Okay? So in the case of the fair coin, you gain exactly 1 bit of information. You insert exactly 1 binary question, because if I ask, has it been tailed? You say no, then I have the answer. I don't need to ask more, just 1 binary question. Or if I place myself before, and let's say you know the answer, Okay, we'll just repeat the same thing. Okay, it's clear what I said? Okay. But now if you write the entropy in log 3 base, for example, it would be the number of questions with 3 possible answers that have been answered. Okay? So now the X bias is a Bernoulli 9/10, and so its entropy is what? Is 1/10 log 2 10 plus 9/10 log 2 10/9. And if you compute that, it is actually close to 0.47, which is close to 0.5. So in average, this biased coin brings half of the information brought by the fair coin. Or it is 2 times more predictable, approximately. Okay? Or you would need, in average, half many questions. So if you think about, it doesn't mean anything, half a question, half a binary question. So how do you interpret that? Let's say that now you toss a very large number of biased coins. If you want to predict their outcomes, you would need half of the number of questions you would need for the same experiment but with biased coins. Okay? Because essentially almost half of them you can already predict, around 90% of them you can already predict what it will be. Because it has quite 9/10 to happen. Okay. So you don't need to ask so many questions. Most of them you can guess them already. Okay. Okay, so to summarize, the Shannon entropy of a random variable is what? It can be seen equivalently as the average information content, which means also the expected information gain when observing the outcome of this random variable. Okay. So here it's really an interpretation in terms of information. But an equivalent interpretation, which is more natural if you place yourself before the observation of the outcome, is as a measure of uninformation or lack of knowledge or unpredictability about the random variable. Okay, but it's the same. Okay. Did you prove? And last point: the higher the entropy of a random variable, the less is structured the distribution associated to this random variable. So here, which means that the entropy is the highest when the distribution is uniform. But if it starts to be peaked, if you have a structure, then the entropy reduces because the random variable becomes more and more predictable. So can you show that the entropy is the highest for the uniform distribution, and what is the associated value? Did someone did it? So what is the strategy you apply to show that?
Get the expectation.
So what I want to prove is that sum of x of p of x minus is maximized when p of x is equal to what? What is the uniform? It's this. How do you prove that? What is the strategy you apply?
Derive.
Huh?
You can derive.
Yes, you can derive. When you want to know something about a maximum or a minimum or an extremum about a function, you equate the derivative to 0. So here you see these probabilities as parameters. So you can derive, this is h of x with respect to a given p of x for a given x, which is what? It gives log 1 over px plus 1. And you equate this to 0. Okay? And what does it tell you? It tells you that p of x is a constant. Okay? And this constant has to be this by normalization. Okay? It's clear for everyone?
Sir,
Yes.
if we want to find the minimum, we need to derive twice.
If you want to find whether it's a minimum or not.
So here it's this function is concave in p of x. Wait. How do you check if it's concave or convex? Is right. A priori, you should check if it's a maximum or a minimum. Is it concave or convex? This function, this p log 1 over p, which is also minus p log p, is it convex or concave? Is it clear for you what means concave, convex? This is a concave function, this is a convex function. Okay.
You take the second derivative.
Yes.
And then check the sign.
Yes, but here actually you can see directly the log.
Yeah.
The log is what? The log is concave times the linear doesn't change the concave. So this is concave with a minus, it's convex. Okay, so this is convex in P. Okay. So wait, no. No, there is a... I'm saying something wrong because this is the max. What am I saying? I'm saying a stupid thing. Okay, so you just... Sorry?
And the convex like, you just said the opposite.
I said the opposite?
Concave and convex.
So this is concave. Then if you take minus a concave function, it's convex.
So convex and concave, like the minimum and the maximum, when you're approaching this, it's supposed to be concave, and this is supposed to be convex. So it's really concave.
No, this is a concave function, and this is a convex function.
I think it's wrong.
No, it's this I'm sure.
I'm probably wrong.
This I'm totally sure. But no, wait. Are we looking for the convexity?
No, yeah, okay, concave. Concave or convex.
I don't know, wait, if I do the product, okay, so wait. I don't know. Okay, so let's, I think I'm saying if you do the product here now, I have a doubt that you maintain the concavity. When you sum convex functions, it remains convex. But wait, so check, you should compute the second derivative in P. So what is the second derivative?
minus 1 over px.
Minus 1 over px, you say?
Yes, sir.
Because this is 1 over p squared minus 1 over p squared over 1 over p. So yes, I agree with you. And this is positive or negative? Negative. Okay. So it is a concave function of p. So I was saying a mistake. The mistake I was saying is that if you multiply a concave and a concave function, it's not necessarily concave. Okay. When you sum concave functions, it remains concave, or if you sum convex functions, it remains convex. Not when you do products. That was my
I
mistake.
think it says that P is convex, so.
Yeah, it's convex, so it has a maximum. And indeed, here, this.
No, convex means that it has a minimum.
Ah, no, yes, sorry. We proved that it is convex and totally lost. We proved that it's 1.
That's what I'm saying.
No, the second derivative. Yeah, so wait.
That's what I'm saying.
No, so there is a. We do a mistake. What is the mistake? Okay. No, it's okay. It's a maximum. It's a concave function. The second derivative is negative, so it's a concave function. And this is a maximum.
Yes.
So it's fine. Sorry. Okay. Okay.
So that means the argument mass of h of x equals 1 over absolute.
No, h of x is h of x is not just. Yes, if you. It's a function of a vector. Here, the vector are p of x1, p of x, last possible outcome. You can see that as a function of vector of probabilities. And the argument is given by the constant vector with value 1 over the cardinal.
Argument max.
If you want, it's the argmax, yes. It's the argmax of this function of a vector. Okay. Yes. So when the distribution is flat, okay, the entropy is maximum. Okay. Now, another property is that this entropy is always what? What is the? Sorry. So now we know it's not always less than 1. We know now what is the maximum value. It is the value corresponding to the uniform distribution. And what is the entropy associated to uniform distribution? So it's, we compute it, it's sum over x of 1 over cardinal of log of 1 over cardinal. Sorry, 1 over cardinal. Okay, and this is what? This is just the log of the cardinal. And this is the formula, this is Boltzmann formula. Here, this is the number of configurations, it's the log of W. You recognize?
Yes.
And indeed, in the case where all microstates have uniform weight, which is the definition of the microcanonical ensemble, the entropy is just the log of the number of configurations. And here is the same. When the random variable has uniform distribution, its entropy is just the log of its number of outcomes. Okay? So this is, we recover Boltzmann entropy. Yes?
You forget the minus or not. Because it's in log of 1 over.
Yeah, but 1 over x, 1 over cardinal is cardinal.
Okay. Yeah.
Yes. Thanks. So the entropy is always less than the log of the cardinal of the space of configurations of the random variable. Okay? And what is its minimum value? It is also bounded from below by, yes, by 0. Because you see that this P, and this is only true in the discrete case. Huh? In the continuous case, things are a bit more subtle, but you see that this log, this 1 over P here is greater than 1, or at least not less than 1, because this probability is between 0 and 1. Okay? So this log is positive, times something positive, something positive. So you just sum positive terms. So it might be 0. But can it be 0? In which case is it 0?
Why?
What?
No.
I already said it. Huh? I said it before 5 minutes ago. Think, look at the function, in which case can it be 0, under the constraint that this P of x are between 0 and 1. Huh? Oh, yes.
Yes.
Yes, you can.
In this? It is this?
In which case?
One?
Sorry? When there is one outcome, when there is only one possible outcome. So when the random variable is determinist,
Okay.
it means that the probability of x is 1 if x is this special outcome, and it's 0 else. Okay? And in this case, we get zeros for all terms, except the only one for which the probability is 1. So we get 1 times log of 1 divided by 1, which is 0. Okay? So when the random variable is not random, the entropy is 0. It's very clear. We said that the entropy is a measure of information content or equivalently of unpredictability. If the random variable is not random, it is perfectly predictable. So there is no uncertainty. So the entropy must be 0. Or equivalently, if I tell you something which you already know, you gain no information. If I tell you something that you know because it's not random, you have no information gain. So the entropy has to be 0. Okay? Okay. I invite you to think about this LDPC codes for tomorrow that we discussed. Try to this parity check codes, this exercise. Okay? Try to apply a bit what we learned and and we continue tomorrow on the entropy, and then we will converge towards proving from the definition of entropy using a very fundamental principle of what we call the maximum entropy principle, how the Boltzmann distribution appears. Okay, this is where we're trying to go. What we did, we ended today a chapter which was approaching the Gibbs-Boltzmann distribution through a very generic definition of distributions which were factor graphs. And what we started today is a new chapter where we just defined an absolutely fundamental object, which is the entropy. We understood that it's the proper definition of information or uncertainty, equivalently. And how, from this object, can we deduce that the Gibbs-Boltzmann distribution is the proper one to describe complex systems. Okay, this is where we are heading. Okay? Good. See you tomorrow.
Can I ask a question? For the Shannon entropy, the information content is ln 1 over p of that x. How did they Why did they choose Ln?
Okay, that's a very, very good question. Actually, it's the question. So why? So okay, tomorrow I will start from where we start now, and I will give you more properties that are verified by this entropy that suggest very strongly that it's a proper definition of information content. But what you are trying to say is that maybe there are many other functions that have similar properties with similar interpretations that could be good candidate to also be a measure of information. Okay? Maybe instead of taking the expectation of the log of 1 over p, why not taking the expectation of 1 over p squared, which also is an increasing function. It has the same monotonicity as log of 1 over p. Or instead of taking the log, take any increasing function of 1 over p. And what we said seems to generalize, okay? But actually, there are properties that would not be, that are very natural properties of information that would not be verified anymore if you take other functions. One specifically that maybe you can also think about it is the fact that if you compute the entropy of a pair of random variables, whose definition, you can see always a pair of random variables as a single random variable. So you should already know what is the definition. It's the sum over all xy that belongs to x plus y of the joint law. Okay. So this is the information gain when you measure both random variables. Okay, the expected information gain when you measure both. And a very natural property that we want to be true for any meaningful definition of information is that if two random variables, so two things, are independent of each other, then observing both should give you the same information as observing one and the other independently. So one property of the entropy also is that if x and y are independent, then h of xy is equal to h of x plus h of y. The information is additive. When I say information, I mean the Shannon entropy. Now we mean the same thing. The information must be additive for independent random variables. Okay, it's very natural. If when random variable is the fact that I don't know the sun is rising or not, another one is okay. No, this random variable is correlated to many things. So you take two coins, okay, that are independent of each other. To toss one, you measure something. You have an entropy associated to that, which is the information gain you obtain of 1 bit in average when you measure the outcome. You do that for another coin. You have also 1 bit. But then, if you would observe the two together, you should get the same information because they're independent. So knowing one does not bring any information about the other, and vice versa. And this is formalized by what I wrote here. Okay, but if you would take, and this follows from the presence of the logarithm, because try to prove this, and this follows very easily from the fact of this property log of AB is log of A plus log B. So the fact that the log turns products into sums induces the fact that the information becomes additive, because this joint law for independent variable is a product of their marginals, and because you will take a log of a product, you will get a sum, and that's how you can prove this formula. So you need a log. But still, maybe there are other functions for which that could be true. And actually what Shannon proved that I will not discuss in this course, but you can read the article I sent you where I explain it in words, or you can look at my notes where he proved that actually this is really the fundamental definition of information through what we call the source coding theorem, which is something that I invite you to read about. Okay, so it is explained in the article I sent you. Okay, I try to explain it without equations. Okay, so maybe you. But actually, there is a theorem that shows that this is the only function that you should consider for definition of information. Okay. And the proof is absolutely beautiful. And conceptually, it's actually not so complicated. If you read what I sent you, and you take 2 hours to think deeply about it, you can understand. Okay, without equations. That is the idea.
Thank you.
Okay, see you, the others, tomorrow.
Okay.